EL minus sorry EM minus EL, EM minus EL, E by H cut of matrix element of H prime ML, okay, uh, into zero order contribution of L, which may be or may not be function of time. So A naught. So the Schrodinger equation, at least in the first order dependence of lambda, we have found in this way. So where we have expressed uh, the wave function psi t was like that way. Suppose summation over k akt uh, of n e to the power minus I ekt by h. Okay, in the previous class, we have already discussed about the expression of psi t in terms of the orthonormal basis. Okay, in terms of the orthonormal basis, the wave function has two type of time dependence. One is from the unperturbed Hamiltonian, which is like the time evolution of Schrodinger wave function, and another is due to the perturbation, the time dependent perturbation. That means the time dependent perturbing potential in the Hamiltonian, and the effect is the probability coefficient akt. Okay, the probability coefficient akt will be dependent on time. So that's why we have found the probability coefficient ak to be time dependent due to the effect of perturbation. And here we have expressed this akt as the power series of lambda, which is suppose a naught a plus ak1 plus ak2 and so on. And here ak naught is the unperturbed value which is independent on time. Okay, whenever lambda is 0, that means in the absence of perturbation, the probability coefficient was actually time independent, static with time. But whenever the perturbation acts on the system, the probability coefficient becomes dependent on time, and the dependence can be expressed in the power series of lambda. So uh, actually I have made some mistake. You have to write the lambda. That means a0 k of lambda to the power 0. This is lambda to the power 1. This is lambda square and up to higher order of lambda. So we could express the probability coefficient or the time dependence of the probability coefficient as a power series of lambda. That means suppose L equal to 0 to infinity. Okay, ak of L lambda to the power n. In general, we could express the probability coefficient in that way. Okay. However, we have found the Schrodinger equation at the very beginning of this class. I have written the form of Schrodinger equation due to the first order dependence on lambda. It's like that. I is cut al dot, which is function of time, is equal to summation over suppose m. Okay, summation over m, then e to the power I el minus mt by h cut. Okay, matrix element of h prime lm, then m. In general, suppose this is first order dependence. It is due to first order dependence. We have found this one. Now in today's class, we shall discuss about some specific system, and following this Schrodinger equation, following this Schrodinger equation, we are going to analyze the dynamics of those system under this time dependent perturbing potential. Okay. But before jumping to the discussion about those specific systems, we have to study about some interesting phenomena, and the phenomena which is already discussed, but today we have to proceed further. Okay, and this phenomena is transition.
साहिल लेला
Transition of the system. Transition of the system. So you have already known what is transition. Suppose you can think of some atomic energy levels. This is suppose ground state. This is first excited state. This is second excited state, and so on. Suppose the system or the electron, atomic electron, was in the ground state initially here. So the initial uh, state of the system is suppose 1. Now you allow some disturbance. Okay, if you allow some perturbation or disturbance passing through the system or passing through the atomic levels, then the electron can absorb the energy from the perturbing Hamiltonian or the perturbing potential. And after absorbing the energy, it will tend to transit to the higher energy levels or the higher energy states. As a result, the final wave function, it may be the linear combination of higher energy levels or maybe specifically one energy level, whatever it may be. So I am writing, suppose this is summation over k, ak of k. K may be 1, 2, 3, 4, any energy. So this is called the transition. This is called transition. Transition means transformation of the system from one initial state to the final state. This is generally called transition. Okay. And you have already studied this phenomenon. Due to the transition, uh, you can explain the atomic spectrum. Atomic spectrum. Okay. For hydrogen spectrum, you have found several spectral lines like Lyman series, Balmer series, Bastian series, Brackett, Foon, Humphreys. All of these spectral lines can be demonstrated or can be explained through this transition process from one initial state to the final initial state. So this is very known to all of you. Okay, from one initial atomic energy level, the system or the electron would jump into another energy level or another the linear combination of stationary states. And due to this phenomena, due to this transition, you can find some spectra, and it is it will be said that the spectral lines, the explanation of spectral lines can be found from this transition phenomenon. Okay, but in some cases you may find some different kind of transition. In some cases you can find some different kind of transition which can make the situation interesting and complicated also. Situation interesting and also complicated. Okay. The previous version of transition is very simple. You have one initial state, and the system jumps into another final state, which is very simple kind of transition. But in some cases, you can find some different kind of transition. I am going to this one where the situation is very interesting and also very complicated for calculation, because you can find some transition from one initial state I to a part of to a state which is the part of continuum. A part of continuum states. The initial state is a single discrete state, but the final state is not the single state or the linear combination of single states. It's the part of continuum state. The final state is the part of continuum state. Uh, and thus, such kind of transition is not the similar we have learned in the previous quantum mechanical classes, which was very simple. But it is not done. It is actually not done before, because this is a different kind of transition. The initial state is okay; it's a discrete state. But after transition, the system will turn into or system will reach into a state which is not a single discrete state, rather it is the part of some continuum states. Okay. And what is continuum state? What is continuum? What is continuum state? Continuum states, you can say that the states of a free particle. In one sentence or some words, you can say that what is continuum states? The quantum states of a free particle. Okay, quantum states of a free particle. Because you know, for free particle, the energy levels, the energy of kinetic. That means E equals to E square by twice for free particle. That means P equals to root over of twice me. Okay. As energy is continuous, so the momentum will be continuous. Okay. So the momentum will be continuous. So for a free particle, suppose this one is a 3 point mass or 3 point particle with mass m. It has no discrete momentum levels. The momentum is continuous. The momentum is continuous. Okay. Thus, the corresponding states, the corresponding quantum state. Suppose you can say that this is a momentum state. Suppose momentum state. You cannot assign some quantum number corresponding to the momentum states, because the momentum is continuous. It is not discrete or quantized. Okay, so you cannot assign some corresponding quantum number. So in this case, these states can be said to be the part of a continuum. Okay, such states can be defined as the part of a continuum. So actually, in this case, you cannot define the exact momenta of the system because momenta is continuous. But you can say that there is a range of momenta. Okay, the range of momenta. Suppose you can say that from
তাহলে স্যার এটাকে
E to হ্যাঁ
পিওরলি থ্রি পার্টিকেলের
বলো
বলা যাবে না।
থ্রি পার্টিকেল তো অবশ্যই থ্রি পার্টিকেল বলেই তো তার এনার্জিটা
তার ফার্স্ট স্টেট আর ফাইনাল স্টেটের মধ্যে তো ডিসক্রিটনেস রয়েছে।
কিরকম যেমন বলো?
বলছি একটা পার্টিকেল ফার্স্টে যে স্টেটে ছিল থেকে আমাদের
আমি বলছি যে ধরো ধরো কোন একটা পার্টিকেল তার এনার্জি সে হচ্ছে ফ্রি পার্টিকেল, ঠিক আছে, তাহলে তার মোমেন্টাম তো যা খুশি হতে পারে না, সে 0 হতে পারে, 0.1 হতে পারে, 0.001 হতে পারে, মানে ডিসক্রিট নয়, তাই না?
ফাইনাল স্টেটে যাওয়ার
তাই
পরে তাকে ফ্রি পার্টিকেল।
না, সেটা এমনিতেই ফ্রি পার্টিকেল, তার মোমেন্টটা তো কন্টিনিউয়াস। তো মোমেন্টটা যেহেতু কন্টিনিউয়াস, তো সেটা তার সেটাকেই বলা হচ্ছে তার যে করেসপন্ডিং কোয়ান্টাম লেভেলস, সেগুলোকেই বলা হচ্ছে কন্টিনিউয়াস।
না,
বুঝতে পারবে ডিউ টু
পার্টারবেশন দেওয়ার আগে তো সেটা ফ্রি পার্টিকেল ছিল না।
এখানে পার্টারবেশনের কথা এখানে আসে। ওকে, এটা আমি এমনি বলছি যে ইটস এ ফ্রি পার্টিকেল, মানে আমি কন্টিনিউম জিনিসটা কি বোঝানোর চেষ্টা করছি। মানে আমি এখনো কিন্তু এই পার্টারবেশনের যে ইফেক্ট সেটাতে আসিনি, আমি আসছি যে হোয়াট ইজ কন্টিনিউম স্টেট অ্যাকচুয়ালি। ওকে, সো আই এম ট্রাইং টু generalize what the quantum states are. Okay. What do you mean by continuum states? Okay, so uh, in order to make you understand, I have taken some examples. The examples of free particle. Okay. If you take some free particle, its energy is purely kinetic. That's why the momentum is continuous. So you cannot make the discrete energy levels or discrete momentum levels. Okay, so that's why such quantum levels of a free particle is called the continuum. But you can say that suppose you have a system, you have a free particle having range of momentum from P1 to P. Okay, this is suppose momentum scale, and this is P1 and this is P2. So there may be infinite number of yes, okay, there may be infinite number of continuum states and they are continuous also. So actually, in true sense, you cannot count the continuum states. It is impossible to count to the number of continuum states between any range from P1 to P. Okay, but this makes the situation very complicated. Okay, now come back to the perturbation. I am claiming that in such case of transition where the system transits from I to some part of continuum state which is F. Suppose it is transiting from I to some part of continuum states in the momentum range from P1 to P2. Okay. So the system transits from I to here. Okay. And if the number of states is uncountable, that means you cannot count the number of states, so how can you find the probability or the transition probability of this situation? So this makes the situation very complicated. Okay, this is interesting of course, but whenever the transition is from such one state to the part of continuum where the number of continuum state is not countable, in this case the situation is really in true sense very difficult and complicated. But here you can use some useful trick or useful mathematical tool. The tool is called the box regularization. Box regularization. Okay, you have already followed this method during your graduation, where you can you could normalize the wave function of a free particle using this method, the box regularization. Okay, because you know that the wave function of a free particle is not localized. Okay, so that's why you have to use this method called box regularization. Okay. So in this case, suppose you could think of the whole system, uh, you could think of the whole system to be a big box. Okay, and big box of dimension L, dimension L with L tends to be infinity. So the whole system is put in a huge dimensional box. A box having large dimension, but it's L. But in the limit, L goes to infinity. Okay. Now, if you put a free particle within such box, then the situation is like one dimensional potential or two or three dimensional potential boxes. And here you can count the number of continuums, because in this case you can find the momentum to be quantized kn equal to n pi by l, right? Kn equal to n pi by l, infinite potential box. Okay, if you put the free particle within an infinite potential box, but the box having the dimension is very high, l tends to infinity. In this case, you can count the number of continuum state in this way. One continuum state is from minus pi by l to plus pi by l, then minus pi by 2l to plus pi, sorry, minus 2 pi by l to plus 2 pi by l. So one of such cell, you can say, it represents the one continuum states, and here l tends to infinity, so thus the cell is very small. The continuum states uh, are almost continuous, but in this case, using the box regularization process, you can count the number of state between the some specific range. Okay, and also you can count the number of state by integration GEDE or GPDP from P1 to P2, where GP is the density of state. As this GP is now defined using the box regularization process, thus you can count the total number of continuum state in that way. So following this box regularization method, you can count the continuum state. Thus, the complicated situation can be resolved where the transition is from one initial state to the part of continuum state. Okay, and in such situation, actually you have to find the transition probability, right? Transition probability. So suppose the transition is from I to F, then the transition probability from I to F is defined by Fi mod square. Okay, is it known to all of you? This is the definition of transition probability, right? Is it okay? Please respond.
Yes.
So this is the formula or expression of transition probability from I to A. Now the situation is, suppose this is from I to some F which is part of continuum. Then this F is not a single state. F lies between some range, between some energy range or between some momentum range, whatever it may be. So in this case, uh, the total transition probability from I to F, that would be summation over all the transitions. That means summation over I mod of Fi of suppose this is J to be precise. So summation over J, this is Fji mod square. Okay. Fgi mod square. Now I am writing in primary sense I am writing it in a discrete, but actually these states are not discrete. Okay, these states are very continuous. Even after box regularization, in the limit L tends to infinity, the speeds. Yes, exactly. So exactly, you can write this one. Actually, this transition probability from I to the continuum state, continuum of A. This is integration. Suppose over energy. Okay, from energy F having energy E to I mod square, and after after simplification of this one, you can add or you can incorporate the density of state. Suppose this is rho e. Rho e f of e I e, and the range may be from suppose e1 to e2. So this is the expression of transition probability whenever you found the transition from one initial state to the continuum state. You have to make the integration over all the continuum states and within the specific range to calculate the transition probability in that way. Okay. So this is the process. This is the process of counting the transition probability. Okay, mod square. I'm missing this one. So the transition probability, the expression of transition probability will be that. So till now, have you any question? Any sort of question you can ask.
No, sir.
Okay. Actually, I have to illustrate the or demonstrate the ideas of continuum state in with some specific examples, and in the next session or in next part of discussion, okay, I shall come with these examples. But now I have to develop the methodology. I have to develop the tool. How can you find the transition probability of this? So now we have to be specific with some very known system having a constant perturbation. Constant. So the examples of time dependent perturbation is now the constant perturbation. So the name is very what I can say, because we have discussed the examples of time dependent perturbation, but I am saying this is a constant perturbation. So how a constant perturbation be time dependent? So this is the question. Actually, this constant perturbation is regulated, time regulated constant perturbation. Okay. So I have the example of time dependent perturbation, which is time regulated constant perturbation. That means you have a perturbation from t equal to 0 to t equal to t naught, where you have a constant perturbation is suppose v naught, and before t equal to 0 the perturbation is off, and after uh, t equal to t0 the perturbation is off. So such uh, perturbation you can say it is the time regulated constant perturbation. Okay. So in this case I have to calculate the transition probability. Okay. In this case I have to calculate the transition probability. So without any other type of thinking, we can directly write the Schrodinger equation in this case. And you know the Schrodinger equation. What is Schrodinger? The Schrodinger equation is am1 dot is equal to summation over n e to the power I em minus n t by h cut h prime of mn n naught. Okay. So here the situation is like that. Initially the system is at I. Initially the system is at I. And after this time regulated perturbation, the system will transit into some part of continuum state. We don't know actually how much it could reach in the final state. But in general, I am saying it is transiting to the final state, which may be the part of continuum state.
স্যার
So
যে
in this
কোনো
case,
যে কোনো কনস্ট্যান্ট পারটারবেশনকে তো তাহলে টাইম রেগুলেটেড বলা যায়।
যদি সেটা একটা পার্টিকুলার টাইমের পরে বন্ধ হয়ে যায় তবে, যদি সেটা কন্টিনিউ কন্টিনিউ চলতে থাকে তাহলে সেটা নয়। ঠিক আছে, আমি কনস্ট্যান্ট ফোর্স যদি কন্টিনিউ টাইমের সঙ্গে সঙ্গে ফিক্স থাকে তাহলে সেটা টাইম রেগুলেটেড কনস্ট্যান্ট পারটারবেশন হবে। এটাকে আমি রেগুলেট করতে পারবো যে কতক্ষণ ধরে আমি রাখতে চাইছি, সেই জন্য এটা টাইম রেগুলেটেড। সো এখানে আমি যদি বের করতে চাই, দিস ইজ আইএইচ কাট অফ এএফ which is summation over n, that means summation over n e to the power I ef minus en t by h cut h prime of f n a n naught. So this is the equation for this particular case. Okay. And now, of course, you can say that this a n naught, okay, this is a n naught is 1 for n equal to I, because the system is initially at I state, so ai naught equals to 1. And for other cases, that means for I naught, n not equals to I, this one is actually 0. So n naught is 1, n naught is 0 except I n equal to I, n equal to I ছাড়া আর বাকি সমস্ত কেসে এই কোএফিসিয়েন্ট গুলো 0 হবে। And suppose this h prime fi is equal to v naught, this is constant, this is v naught. Okay, h prime is a very constant potential, so this is v naught. So you can write a ih cut f1 dot is equal to, you have only one term which is e to the power I m minus ei d by h cut. Okay. This is v and this is ai naught, ai naught. Now suppose ef minus ei by h cut is suppose omega, this is omega, that means e to the power I omega t v m. Now af of 1, it will be 1 by v, actually v is constant, so you can write v ai naught by ih cut integration e to the power I omega t, and the integration limit is from 0 to t naught. The perturbation is on for on in the time interval from 0 to t naught. So that's why the expression of a in the first order, of course the first order correction of a is equal to that, because af 0, af naught is basically 0, because initially the system is in the ith state, so ai naught is equal to 1, otherwise for other states the coefficient was actually 0. So that's why af naught, so af t is equal to af naught plus f1 lambda, right, up to first order. So up to first order this is 0, so you can write af of t is equal to lambda of that one, lambda v ai naught by ih cut. Okay. ih cut, and this integration will be e to the power I omega t, e to the power I omega t by I omega, a limit from 0 to t. Okay. So this is ft. and after putting the limit I will be minus 1, so lambda v ai naught by minus h cut omega e to the power I omega t naught minus 1. Okay, you can write this one. Now you can take common as e to the power lambda v ai naught e to the power I omega t naught by 2 by minus h cut omega. Now you have e to the power I omega t naught by 2, which is twice I sin omega t naught by 2, right? So f t naught basically after t naught, or f t greater than t naught, because after t naught the f becomes time independent. Okay, the variation, sorry, the variation of t is from 0 to t naught. After t naught the situation or the system goes to uh, the static one. Okay. So after t greater than t naught, af t greater than t naught is equal to that. That means this one. Okay. Twice I. So twice I lambda v, twice I lambda t naught, okay, by minus h cut omega e to the power ai naught, sir. Ai naught e to the power minus e to the power I omega t naught by 2 by h cut omega minus h cut omega sin omega t naught by 2. Okay. So this is the expression of F. Now the transition probability. Transition probability should be Fi mod square, which is actually this will be 4 lambda mod lambda square mod of E naught square ai naught square by h cut square omega square of sin square omega t naught by 2. Okay, sin square omega t naught by 2. So this is the transition probability, but it is not the complete transition probability because I have taken only single f, but actually this transition is from I to the continuum f, which is the part of continuum. Then the transition probability should be written t from I to f is equal to integration of rho of e, okay, rho of e, this one, mod square of e. Okay. Now suppose this whole thing is a constant. This is suppose capital A. Okay. This is capital A. So capital A rho e sin square omega t naught by 2 into t. Okay, so now you can write this is rho e sin square omega t naught, okay, omega t naught by 2 by omega t naught by 2 whole square, okay, omega t naught by 2 whole square into এটাকে আমি আবার কনস্ট্যান্ট ধরে নিলাম এই জায়গায়, তাহলে থাকছে কি না সাম বি টি নট স্কয়ার, okay, de. So this is a sinc function, right? This is a Sync function. So the whole of this thing will be dominant if omega tends to 0. Whenever omega tends to 0, then sine of that one, sine x by x in the limit x tends to 0 to be 1. Otherwise, in other cases, the value of this portion dies very quickly. So that's why the transition will be dominant. The transition will be dominant if omega tends to 0. If omega tends to 0, then this portion will be of some significant value. The transition probability will be significant. Otherwise, if omega not equal to 0, then the whole thing is very negligible numerical value. Okay, because you know the plot of this sin x by x like that sync function. Okay, so the principal maxima is very high and it covers most of this area, and the other portion is very negligible, very insignificant. So that's why the transition will be dominant whenever omega tends to 0. So that's why we can claim that the transition will be dominant when the energy of final state and the initial state is very similar. Okay, omega tends to 0 means EF tends to EI. So this transition does not support the change of energy. Okay, this transition happens whenever that initial state and a final state having the same energy eigenvalue. Okay, and in this case you can calculate this integration in the limit of omega tends to 0. So that's why you can say that t from I to f is proportional to t square. This is proportional to t square. Okay. And of course, we have to write this integration will be performed when E will go to EF, and this EF is nearly equal to EI. So this is proportional to T naught square rho of E goes to EI. So the transition probability is that then the transition rate omega, which is T I to F by T naught, which is equal to alpha T naught rho, and this is called the Fermi's golden rule for constant particles. The transition rate is proportional to the density of state near about the initial state. So the transition will happen uh, in the states nearing the initial state. Okay, in different levels. That means whenever the energy difference between the initial and final state is very high, then the transition will become the insignificant. The transition rate is dominant whenever final state energy nearing the initial state, and in this case it will be proportional to the rho of that density of that energy. So this is called the Fermi's golden Fermi's. So this is an example of time dependent pattern. Now you have to express the actually the physical aspects or physical outcomes of such constant perturbation. Okay, so in the next slide. So constant perturbation. So constant perturbation is such a perturbation where it is the transition from initial state to the part of continuum state, which is final state, but the transition probability will be dominant wherever EF goes to EI. Okay, so the transition will happen from the initial state to the those systems which are nearing, which are actually surrounded the initial state. So how can it be possible? The perfect example of constant perturbation is auto ionization. Auto ionization, or it is called the Hogarth transition. Okay, the example is auto ionization, Hogarth transition of helium atom, suppose. So you know the Hamiltonian of helium atom. Helium atom is basically a three body system. It has two electrons and one nucleus. So you can think of the helium as a two hydrogen atom. One is suppose P1 square by twice m. Okay, uh, minus 4 square by, sorry, 2 square, 2 square by 4 pi epsilon naught r1, then p2 square by twice m minus 2 square by 4 pi epsilon naught r2, and the repulsive potential between two electrons, which is e square by 4 pi epsilon naught mod of r1 minus r. Okay, is it okay? The Hamiltonian of the helium atom. R1, suppose this is nucleus, this is one electron having put R1, another electron which is R2. Okay, so the kinetic energy of first one is,
একটাই অরবিটাল থাকে।
hello, একটাতে থাকলেও পজিশন ভেক্টর তো আলাদা হতে পারে। তো আমি জানি না একটাতে থাকবে কিনা, একটাতে নাও থাকতে পারে, ডিপেন্ডিং অন দ্য এক্সাইটেশন। গ্রাউন্ড স্টেটে থাকলে একটাতে থাকবে, কিন্তু পজিশন ভেক্টর তো আলাদা, R1 and R2. Okay. So this is like one hydrogen atom, this is second hydrogen atom. Okay, and this is the non-trivial term. So you can write the Hamiltonian, suppose each is equals to, suppose H1 hydrogen plus H2 hydrogen plus E square by 4 pi epsilon naught mod of R1 minus. So now you can treat this one as a perturbing potential, and for the time being you can uh, pretend that this is a constant, time regulated constant perturbation. So this is the perturbing part of the Hamiltonian, and this too is H naught. Okay, H naught is the combination of two hydrogenic atom Hamiltonian, H1 and H2. This one. Now the energy level of this unperturbed Hamiltonian can be quantized by two quantum number, En1 and En2, and which will be minus 13.6 into 4 by N1 square minus 13.6 into 4 by N2 square. Can I write this one? Z square, okay? The ground state energy of hydrogen is minus 13.6 electron volt. And for helium it will be 4 times, because Z square of minus Z square of hydrogenic ground state. Okay. So the quantized energy level of hydrogen atom, or sorry, unperturbed part helium atom is like that. So if you can make the diagram for energy levels, this is suppose 1 level. What is the value of 1 level? Minus 54.4 and minus 54.4. So minus 108.8 electron volt. Okay. Now the second level is suppose 1 2. What is the value of energy? 1 2. 2 means 4. 2 square means 4. So 4 will be cancelled out. So minus 13.4, sorry, minus 54.4 and minus 13.4. So 30.6 is 67, 68, right? Minus 68 electron. So after this one, suppose you have 1 infinity. 1 infinity means one of the two electrons are free. That means this is uprooted from the orbit. It is now free. Okay. So the energy level 1 infinity it will be minus 54.4, right? And after that you have it is now a continuum state because one electron is free. Okay, and free electron may have the different momentum. Okay, suppose this is just free from the electron. After that, the momentum will be changed continuously. So from here, the continuum states begin. From here, the continuum states begin. Okay, and after that, it may be 2 infinity, 3 infinity, 4 infinity, and it will go to infinity, where the energy level is 0. Okay, then after that, this is the second continuum state. So from here, first continuum state begins, and from here it is completely continuum because infinity means that two electrons is free. Both of the electrons are free, so that's why the system is under completely continuum state. Okay, so this is minus 54.4 electron. Okay, so this is 1 infinity, that means minus 15.4 electron volt. Okay, now if you have two state, now this is two state. The energy level of two state will be minus 13.6 and minus 13.6, which is 27.2 minus 27 point, and this state is not continuum. This is discrete state because two state is discrete, right? This two state is discrete. Now I have only want to concentrate on these states. This is 1 infinity, which is minus 15.4 electron volt. This is infinity, which is having energy 0, and another is two state, which having energy minus 27.2 electron volt. Okay. Now this is a discrete state. This is not a continuum state. Now suppose in some instant a electron initially is here. So ith state is suppose two state. Initial state is two state. Now due to the effect of this perturbing part in the Hamiltonian, it will make transition from I to F. to a p. Now the ideas from the previous discussion, it says that it will make transition from those states which were nearing the initial state. So this 2 state is in the embedded in the continuum states. So that's why this electron will easily coming out from the state and it will transit to this continuum state. Okay, so that's why the helium atom sometimes gets ionized by itself without any external influence, without any external perturbation or any electromagnetic wave passing from. হুম, হ্যাঁ বলো।
আরেকবার কমেন্টে বলুন।
হ্যাঁ মানে আমি বলছি যে ধরো 1 ইনফিনিটি যে স্টেটটা আছে এর এনার্জি লেভেল কত -15.4 আর ইনফিনিটি যে স্টেটটা আছে এনার্জি 0। তাহলে এই এর মাঝখানের যে স্টেটটা এটা কিন্তু কন্টিনিউয়াম স্টেট, তাই তো? এটা বুঝতে পারছো কিনা দেখো, কারণ একটা ইলেকট্রন ফ্রি হয়ে যাওয়া মানে সে তো কন্টিনিউয়াম স্টেট দিচ্ছে, তাই না? মানে ধরো এখানে -15.4, এর পরের এনার্জিটা কি হবে -15.4 প্লাস ইকে অফ দ্য সেকেন্ড ইলেকট্রন। এটা হচ্ছে 0 অফ দ্য সেকেন্ড ইলেকট্রন, কাইনেটিক এনার্জি অফ দ্য সেকেন্ড ইলেকট্রন, তো হুইচ ইজ কন্টিনিউয়াস। তাহলে এর মাঝখানে আরেকটা এনার্জি লেভেল আছে যেটা আমি কার্লি ভাবে এঁকেছি, সেটা হচ্ছে 2 এই 2টার এনার্জি লেভেল হচ্ছে -27.2 ইলেকট্রন ভোল্ট, যেটা ডিসক্রিট। এই এনার্জি লেভেলটা ডিসক্রিট কিন্তু। এবার ধরো কোনো একটা ইলেকট্রন এই 2 লেভেলে আছে, সে সে অটোমেটিক্যালি কি করবে, ট্রানজিট করে যাবে এই এই কন্টিনিউয়াম স্টেটের মধ্যে, কারণ এ তো এমবেডেড হয়ে আছে, তো কাছাকাছি আছে তার মধ্যে, তাই না? আমরা বলেছি যে ট্রানজিশনটা কখন হবে, যে কন্টিনিউয়াম স্টেট গুলোর মধ্যে যখন ইএফ গোজ টু ইআই হবে তখন ট্রানজিশনটা হবে। তাহলে ও তো ইআই, এই ইআইটা তো তোমার ইএফ এর মধ্যেই আছে, এই কন্টিনিউয়াম স্টেটের মধ্যেই তো এমবেডেড হয়ে আছে ইআইটা। তাহলে সে যখন যখন খুশি কিন্তু সে ট্রানজিট করে যেতে পারে। এইটাকেই বলা হয় অটো আয়োনাইজেশন। এই জন্য অনেক সময় হিলিয়াম অ্যাটম নিজে থেকে অটোমেটিক্যালি ট্রানজিট করে যায়, কোন রকম বাইরের ইনফ্লুয়েন্স ছাড়াই নিজে নিজে অটোমেটিক্যালি ট্রানজিট করে যায়। এই ঘটনাকে বলা হয় অটো আয়োনাইজেশন। ঠিক আছে, এটা হচ্ছে কি কনস্ট্যান্ট পারটারবেশনের একটা এক্সাম্পল। দিস ইজ দ্য পারফেক্ট এক্সাম্পল অফ কনস্ট্যান্ট পারটারবেশন। Constant perturbation does not allow the transition which is energy violating. Okay, এই জন্য বলা হয় যে constant perturbation is a energy preserving transition, কারণ এনার্জি প্রিজার্ভ করছে। and the example is auto ionization. এই হচ্ছে constant perturbation। আর নেক্সট ক্লাসে আমরা হারমোনিক পারটারবেশন করব, সেটা নিশ্চয়ই এনার্জি প্রিজার্ভিং হবে না, সেখানে এনার্জি ডিফারেন্ট কাইন্ড অফ এনার্জি লেভেলে জাম্প করতে পারে, সেই ট্রানজিশনটা পরের ক্লাসে।